So the lectures so far for chapter 3 describe the derivation of the thermal resistance, looking at conduction, convection, and contact resistance. We looked at how to account for multi-layer walls when the layers are in series or in parallel. We looked at two different types of parallel arrangements. And then we paid particular attention, in fact, to the straight wall. So we consider one-dimensional problem where temperature only varies along the x direction, which is perpendicular to the wall surface. And we saw that as shown here on the screen, and that comes from the lecture notes on chapter 3. The governing equation is a second-order ordinary differential equation. And we were able to derive the temperature distribution from that and look at the definition of heat flux and the resistance. Okay. I made some slight modification to the slides to add a couple of slides as for chapter 3, which describes effectively what we did during the recorded lectures. And also just to include a summary of the resistance. So we have a resistance for conduction, which is written here, and the derivations are provided and summarized here, and a resistance for convection. So I've added these two slides compared to the overhead that I used during the recorded lecture. Then if you skip to the end, that's where we stopped last time. And after that, I added another 3 slides, which I will cover now briefly. So that's what we have. We have governing equation for planar wall, cylindrical wall, i.e. tubes of finite thickness, and then spherical walls, which I won't go into each time. Each one starts from a different coordinate system, which lends itself well to the geometry. So Cartesian, cylindrical coordinate system, and spherical coordinate system, and that's how we end up with different equations. We saw as an example, for example, for the cylindrical one, that the resistance to heat transfer involves now a logarithmic, a natural log function, where we look at the ratio between the radius of the outer surface and the inner surface of the finite thickness pipe wall. Okay, so that's where we are. We also are going to skip very quickly over the next derivation. You are not expected to be able to rederive this temperature difference that was covered in previous year, but we won't do it now. All I would say is that you have to be able to use the equations that are provided in the formula sheet and that are copied here. They show the way temperature varies as a function of position along the wall. It's the same coordinate system, x equals 0 on the left-hand side and x equal capital L on the right-hand side of the wall, as same definition as we used in the planar wall without the heat source. So the only difference here is that there is a uniform heat generation and dissipation within the wall that raises the temperature in a way that follows a quadratic function. So we have a temperature definition, heat flux through the wall, which is a function of temperature difference as well as heat generated inside the wall. It makes sense. If you're generating heat inside the wall, you're changing the temperature of the wall, therefore you're changing the amount of heat that flows through the wall, because heat flow is governed by temperature differences and then the rate of heat flow. Everything that follows from that page 11 to the end talks about fin extensions. All you have to be able to do is what I will cover now, and you don't necessarily have to be able to rederive anything that happens after page 11 there. You just have to be able to use and understand what I'm going to say now in this recorded lecture, and that's captured in the 3 additional slides that are shown here. Okay, so what do we have? First of all, what is the purpose of a fin? And you have an example there where you have a tube on which fins are added to the tube. And we see that quite extensively in engineering application. And where do they usually happen? If you think a little bit about it, you may have already noticed that generally you get this kind of arrangement when you have a liquid inside the tube, maybe hot or cold, and you've got a gas flow on the outside. And the reason for that is because the H coefficient that's characterizing convection heat transfer is always going to be lower for for vast majority, unless you have a gas that undergoes a phase change, H is always going to be lower for the gas than the liquid. So we extend the surface in order to balance that. And why is that necessary? If you go back to this multi-layer wall, why is it multi-layer? Because you've got a resistance to heat transfer by convection, resistance to heat transfer by conduction inside the wall, and by convection on the other side. So that means if you're representing the thermal process or the process of heat transfer through convection, by convection, conduction, and convection on the inside, you end up with 3 different layers with different resistance due to the different processes taking place. For this kind of cylindrical problem, cylindrical coordinate system, you use the cylindrical coordinate system for the governing equation, and that leads to this different resistance due to conduction. So the total resistance is 1 over the area of surface A, that is on the outside, multiplied by the heat transfer coefficient by convection, H1 on the outside. So that characterized the gas flow if we consider this problem here. Then you've got the conduction, and then you've got the convection on the inside. And if this is liquid, then that would be H for the liquid and A for the liquid. So if it is indeed a problem of liquid inside and gas on the outside, then the liquids will have H. So I'm actually presenting it in the opposite way there. So let's rearrange that because the argument is the same. Okay, so then we're left with H2. So that I don't have to contradict myself. I save this. And I project again. So, okay, so we have a liquid. Just what I'm saying here is that this arrangement there is going to be this one. Therefore, we have a gas on the outside and a liquid on the inside. If we have a liquid on the inside, H is most on the inside. I understand now. The 2 is actually the outside. I got it doubly wrong. Okay, so you may have spotted that. Okay, so apologies. H2 is on the outside, so that's the gas. So H2 is smaller, even though the area on the outside is bigger. When you multiply the two together, you're almost guaranteed that it's going to be a good bit smaller than A1, H1. So what is the result of that? If you make this one much smaller, then the inverse is going to be much bigger than this one. Therefore, really what matters in terms of the resistance, this one can be neglected compared to this one. You're left with the other 2. Okay, so these 2 here. So basically, straight away, we see that if you want to improve or increase the rate of heat transfer from the hot to the cold, you really have to work with perhaps A to H2. Okay, because if you keep on improving this one there, or the convection heat transfer on the inside, it's not going to do much because this one is negligible compared to this one when it comes to calculating the resistance. Remember, the resistance, the bigger it is, the less heat flow you have. So in order to improve heat transfer, you need to reduce the resistance to heat flow. It means in this case, no need to work on this one. It's already negligible. You need to work on this one. So if we had stuck with a gas, you could increase the speed of the fluid flow, and that may increase a little bit H, but it's never going to get as good as the liquid, most likely. So one way of doing it is to increase the area. To increase the area, you stick in fins, or what we call extension, to the area of the surface exposed to the fluid. And it's very clear that's what's happening there. Okay, so that's the purpose of these extensions. You will see them on the side of your multi-layer structure, which has a higher H, and that's almost always the case. Right, so let's now look at the equation. So it's a very busy slide, but it's essentially capturing everything you need to know in order to be able to use the formula that are given to you. Standard flat surface, okay, not the one extended. Forget about the fins here in order to understand this one. Surface area is the area exposed to the fluid without the fin in this case. Convection coefficient is H, we know what it is. The temperature difference that drives heat flow is going to be difference between temperature of the surface and temperature of the fluid away from the surface. We write it in this way. if T infinity is smaller than Ts. So you're right, the delta Ts being the positive temperature difference. The rate of heat transfer, we don't talk about direction of heat flow there because we use everything that's positive. H is positive, area is positive, delta T is positive. You can rewrite it in this way where you use the resistance to heat transfer. So resistance due to convection is going to be defined this way. If that's all we have, just a flat surface exchanging heat with the fluid, in that case, the only mechanism is convection. Good. Okay, so that's the way you would deal with a surface, a normal surface that's not extended. So I've just summarized the various quantities. If you have an extended surface with either a single or multiple fins, so they're called fins, that's why we have an F. For example, if you have n such fins, then the total area exposed to the fluid will be the area of the fins. So total combined area. If AF is the area of a single fin, and you have 10 fins, then the total area of the fins where the solid is exposed to the fluid, that is n times AF. So AF in this case would be the surface here, surface at the top, surface here, on the other side, and on the other side. But typically, very often you neglect that area, you neglect the top and the bottom. It depends on how thin that structure is. Then AB stands for the area of the base, which is not covered by the fins. So it would be this one there and this one here. Okay, so AB is the area not covered by the fin, and AF is the area of the fins. Temperature difference is written instead of delta T, we use the theta Greek letter. Theta B is the temperature from the surface, the base, that is essentially not on the fins, at the base, minus T infinite. The fin efficiency, which is defined as the heat flow through a single fin divided by the maximum possible heat flow through the fin, is well, what we define as the fin efficiency. And what is, to make this very clear, what is the maximum heat that the fin can effect? It's the heat transfer from the fin that could be achieved if all of the fin was at the temperature of the base, right? You have a resistance to heat transfer through the fin because of conduction. So it means that not all of the fin will be at the same temperature of the base. If you want to effect maximum heat transfer from the fin to the fluid, that means the fin is at higher temperature, you will need to maintain the fin at the same maximum temperature as you have at the base. But the temperature decreases gradually because of conduction. It gets cooled by the fluid. So the tip of the fin is not going to exchange as much heat as the base. But if you have very, very good thermal conduction, you may achieve a fin that is at the same temperature everywhere. Or if you have a fin that's extremely thin, that's simplifying it. Let's just say that it's able to transfer the heat by conduction very fast compared to the heat that's taken away by convection. In a way, you don't need to get into all these details, because if you have a value for the fin efficiency, you know essentially by how much heat is affected by the fin compared to the maximum. The maximum is defined using the formula that are here in a very simple way. It's going to be H, we assume the H is not affected by the presence of the fin, multiplied by the area of the fin, and we assume that all of the fin is at the temperature TB. So the heat transfer affected by that ideal fin is the one that's governed by the temperature difference theta B, that is temperature at the base minus temperature of the fluid. So if you've got eta F, you just use that formula. When we have to have H, we have to have the area of the fin, and we have to know the temperature of the base and the free stream. And in that case, you can calculate from eta F the actual heat transferred by one single fin. But obviously, we don't just have one fin. Okay, we have a number of them in most practical engineering applications, so we need to account for the combined effect of all these fins. And we can prove, and it's reasonably easy, we normally do it, that the efficiency of the whole array is defined by that. You need to know the efficiency of a single fin, you need to know how many fins, the total area, which is this one, and you get your efficiency of the array. So how do you work with that? Simply with this here, okay? I'll wait till that disappears. So delta T here is actually theta B. It's the same thing. So let's actually write that now. Can define Okay, they are the same in this case. Right, so once you have the resistance of the array, which is defined in terms of the efficiency of the array and the total area, you can get from the temperature difference the rate of heat flow. So it's all good. This is all you will need to have to know. Essentially, you'll have to know how to use it in order to take account the effect of the array. How do you get the efficiency of a single fin? We can prove that, but we won't. Just take the formula at face value. It's in the formula sheet. I'll show you where. You calculate it from the hyperbolic tangents. In the normal calculator, you press the key, which is HYP, and then the tan function. You end up with the hyperbolic tangent. In Excel, you write equal tan H brackets and it pulls out the hyperbolic tangent formulation. Capital M is defined not here, but just above in the formula sheets. LC is the corrected length, and that's what I need to explain now. This formula is true only for an adiabatic tip condition, which means there is no heat loss through the top tip. Either it's perfectly insulated, or simply it's long enough to assume that the temperature here is actually quite close to the temperature of the free stream, and you don't really have much heat left anymore. Generally, you can use that for all condition, even those that are non-adiabatic tip, and that's why we use a correction, because generally you don't have an exactly adiabatic tip condition, so you correct the length, you increase it a little bit more in order to account for that inaccuracy, and that's done by, in a square or rectangular fin like this one, adding half of the thickness. The area is not calculated from that corrected length. Oh yeah, sorry, it is. You calculate it from the corrected length, 2W multiplied by LC. And you see that essentially counts for the area of the tip. But we don't calculate the area of that side and the area of that side. We assume it's thin enough. You've got triangular formula, parabolic formula. They get a bit more complicated. These are some form of Bessel function. So you can't actually calculate them in an exam situation. So instead, what you can use from the formula sheets is a graph. So second page, you see this is the diabatic. You see the exact rate of heat transfer. And from that, you can infer the efficiency, which is actually given here. You see the definition of M that you have to be able to calculate. And capital M is used for some other calculations there. Just pointing out that the square root stops just before the theta b. Area AC is the area of the cross section, so it would be the area of that flat surface you see in picking here. That would be AC. If you have, that's for a constant cross section, uniform cross section. So there is a single AC defined. If you move to these more exotic shape, the area of the cross section changes. And that's why this capital M is not used anymore at any stage. If you have a non-constant cross section, you can use these graphs instead of the formula. Okay. So let's finish with these lectures. We've covered all you need to know. And essentially what we're not going to do is the derivation of the fin equation itself. So the derivation of the efficiency of a constant cross-section fin. And it also means that one of the tutorials is not going to be covered. It's tutorial, I'll discuss it this afternoon during the tutorial session.